Hello, everyone. Good afternoon, good morning, good evening, and welcome to this MPS webinar session on intelligent power solutions for next-gen robotics platforms. Without any further delay, let me start with the agenda. So first, today I'll start with the general robotics market growth. What are the key economic and technological drivers? And then move on to why we focus on the SoC platforms today. And as MPS is a power management solutions company, then we move on to the challenges in powering these high performance compute SoCs in robotics, and then talk briefly about the MPS key technology differentiators, and then we then move on to the controller plus driver MOS plus point of load solutions for intelligent power management, and then we wrap it up for the Q&A. So, starting with the robotics market growth and with a bigger picture on the market growth. So, what is driving this economically? The humanoid robotics market is still emerging, but it is projected to roughly reach around $3 billion US by 2035, and this signals long-term commercial potential. And the key driver behind this growth is the increasing demand for automation, particularly in manufacturing. And the goal here is to improve efficiency, reduce errors, and also maintain consistent output. And for this, robots are essential to achieve these goals. So at the same time, what we see is persistent labor shortages in economies around the world, and aging population, and also declining workforce that are contributing to this. So there aren't simply enough workers to fill the repetitive or physically dangerous or demanding roles, and also other factors like rising labor costs and etc. So also adoption here extends beyond the traditional use cases. So for example, we see robotics in healthcare, retail, logistics, and this broadens the whole addressable market. Okay, so shifting from the economic drivers to the core technological drivers that enable this massive growth. So, at the heart of all this, the first one is physical AI, especially powered by edge compute. So, instead of relying on the cloud, robots can now process vision, perception, and also decision making locally on the device itself. So, this is critical for real time responsiveness, safety, and also autonomy. And the next one is so this is also supported by advances in sensor technology. So, because modern robotic systems have to combine inputs from cameras, radar, LiDAR, and even tactile sensors. And so this allows them to better understand and interact with complex dynamic environments. And another enabler is electrification. And with electrification, with improvements in battery technology, this is making robots more mobile and energy efficient. And this expands their usability across different domains. And also at the same time, the high performance compute SoCs that includes the GPUs, the dedicated AI accelerators, and these are all driving a massive increase in the on-device processing capability, which is essential for running advanced AI models directly on the robotic system architecture. And more importantly, all of this happens alongside miniaturization, which means we have to keep on packing more capabilities into more smaller and more practical form factors. So the robotic system architecture of today is at the convergence of AI, sensing, compute, and also power efficiency. So what MPS does to enable this market? let's look at that. So now connecting all this to how MPS is positioned to enable robotic systems. So robotic systems in general are fundamentally complex from a power architecture standpoint because multiple systems have to work together. So, for example, actuators and drivers. So, these are the core of motion. And so, MPS has a wide portfolio of actuators and drives. So, from motors, motor drivers, servo controllers, angular sensors, power modules, and also isolated gate drivers, isolated DC-DCs, digital isolators, current sensors, and silicon carbide MOSFETs as well. And all of this provide highly efficient solutions that enable precise control and smooth motion, and also better energy efficiency, which is critical for both the industrial and the humanoid robotics. And the next one is battery management. And as robots become more mobile and electrified, a comprehensive battery management portfolio is also essential. And so MPS has advanced solutions for this. So we have battery monitors, protectors, fuel gauges, and also active balances. And so this improves overall the runtime and also the system reliability. And last but not the least, the compute part. So the major driver, the high performance compute and AI accelerators that require stable and efficient power delivery. So our portfolio has a wide range of the multi-phase digital controllers, the IntelliPhase driver MOS, the POL point of loads, and also Intelli modules that supply to the core rails of the robotic SoC platform. Yeah, so in summary, whether it's motion, intelligence, or energy storage, we have all the solutions that will enable customers to design a very scalable and an efficient and also a reliable robotic system. So moving on to the robotic SoC platform. So why are we focusing on the SoC platform today? So the SoC platform mainly forms the brain of the robotic system architecture because perception, decision making, and control all come together at the brain of the robot. So as robots are becoming more autonomous, more intelligent, and more responsive, the demands on these SoCs also increase significantly. And so now taking a look at a humanoid robotic SoC, there are several key components. So, for example, the CPU to handle any general purpose processing and control logic. And next, the GPU or AI accelerator that is responsible for heavy workloads like computer vision, object detection, and machine learning and also machine learning inference. And also memory subsystems that are needed to support high data throughput, especially with the working with the high resolution sensor data in real time, and also I/O interfaces to connect. So all of these components together make the SoC very, very compute intensive. And processing the multiple sensor streams, running AI models, and making real-time decisions also require significant processing power. So with this significant processing power also comes high power consumption. And these platforms turn out to not only be power hungry, but also require precise and efficient power delivery to maintain the performance, manage thermals, and also extend battery life. And that is why the SoC here is the key focal point. And because at MPS, we specialize in power management solutions. So let's take a look on what are the challenges in powering these robotic SoCs one by one. So first one is these systems are heavily battery dominated, and also there's limited energy budget and also need for longer run times. So the power management solution that you choose has to have certain features like sleep mode, low quiescent current, and also phase shading techniques that help to extend operating times and conserve energy. And also, so for the next one is that smaller form factors. So here systems shrink, but the batteries remain bulky and more power must be delivered. So the solution here is advanced packaging and integration technologies that enable these smaller form factors. And the next one is dynamic workload. So these high performance compute SoCs or AI SoCs switch rapidly between different workloads, and the voltage regulators that we deploy should respond immediately to the sudden current spikes, which in turn means must have faster transient responses. And the next one is thermal management. And due to the absence of any heat sinks or fans in a robotic system, and also limited airflow from the head to torso, so the solution should deliver high currents with minimal losses without overheating or damaging the system. Yeah. So coming to what solutions or what key technologies that MPS has in terms of mitigating these challenges in powering the robotic SoCs. So the first one is the advanced integration technology that enable higher efficiency and also smaller form factors. So, when we come to SoC power management, so SoC power management definitely needs higher integration compared to the legacy analog approach, where we have the gate drivers, the current and temperature sensor, the MOSFETs, all on separate die, but on the same package. We have a more integrated digital approach where we have the high side, low side FETs, the gate drivers, the control logic, the current sensing, so everything in one die. So with this integration, in addition to having a smaller form factor, so we also achieve huge benefits in terms of higher power density, better efficiency and reliability, and because it's all inbuilt, the current sensing and temperature sensing is also more accurate. So coming to MPS's proprietary monolithic driver MOS design. So on the left, we have a legacy 5-die solution, and on the right, we have the monolithic 1-die solution. So with the MPS driver MOS, we use the monolithic design where everything is on a single die in a single package. And this technology helps to reduce propagation delays as well as dead time. So the background is this is done by having many single drivers that drive parts of each MOSFET. So here, each MOSFET will consist of many single, simple, smaller MOSFET cells, and they are all set parallel. And some of them will have a dedicated driver, and this contributes to the shorter dead times and delay times because having many drivers for parts of a single MOSFET also allows you to switch off parts of the FET. So this in turn increases your light load efficiency and also minimizes your switching losses. So in summary, the monolithic design has incredible benefits in addition to achieving smaller form factors. And also due to the higher current demands in, for example, in an advanced robotic SoC platform, a monolithic design will bear more benefits than a discrete solution. Okay, so next, coming to how we tackle these dynamic workloads. So we'll go a bit deeper into the advanced PWM techniques that our controllers use. So traditionally, PWM control, for example, for peak current mode control. So this is a two-stage feedback system. So in current mode control, there is an outer voltage loop and an inner current loop. And the outer voltage loop reacts to the output voltage error, and this appears after output current changes, and this adds delay. And next is compensation. So this also requires additional compensation circuitry to maintain stability. And also fixed frequency operation. The PWM cycles are based on fixed switching frequency. So even if load step happens suddenly, the correction only happens at the next switching cycle and not instantly. And so to tackle this problem, what we introduce is MPS Advanced Constant On-Time PWM control, or adaptive constant on-time PWM control, as we call it. So here, this chord control algorithm, it maintains a fixed on-time for the high side switch, but the output voltage determines when the next on-time pulse begins. So this naturally adapts to any load changes, which in turn gives rise to a faster transient response. So because the off time adjusts dynamically, it's able to maintain better regulation. So this is partially a variable frequency operation, and that adapts to the necessary load condition. And also, another benefit is that it stabilizes the control loop without the need for external compensation. So in conclusion, there's a benefit of a faster transient response to load step, and also reduction with the output capacitors as well. Okay, so the next benefit, so when it comes to multi-phase digital controllers, so here, for example, we see the inductor current of each phase, IL1 and IL2. They increase in pattern of quick, small steps. So here you can see there is a better and a dynamic current sharing. So there's no leading or lagging between the phases, and it's much more uniform, and it's much more dynamic and a better current sharing methodology than the voltage or current mode control. Okay, so the next one, what are the power management schemes that the MPS solutions have to extend battery life? Okay, so the first one, what are the requirements that these ICs should have? So is of course low quiescent current. So having lower quiescent currents will lower your overall average system's current consumption by lowering the current consumption in an idle or a sleep state. And the next one is the necessity to have configurable modes of operation, both DCM and CCM. So DCM under light load conditions. So this will lead to adjusting your switching frequency, leads to lower switching frequencies, and this will significantly then also decrease your switching losses. Also, continuous conduction mode, because then this lowers the RMS current flowing to the converter, and which inherently then reduces your conduction losses. Also should support adaptive voltage scaling and dynamic voltage scaling. So for example, AVS is your IC's ability to follow the voltage setting that is required. And DVS, the dynamic voltage scaling, will adjust your converter's output voltage on the fly. So this will adopt then to the SOC or the FPGA demand. And also phase shedding and phase adding schemes, because when you have higher loads, you need to have more phases, and when you have lighter loads, you have to automatically shed your phases. So phase shedding or phase adding, depending on the output current. Okay, so coming next to how we tackle thermal management. So coming to our process and package technologies that enable efficient thermal management. Okay, so at MPS, we use the BCD Gen 6 process technology, but we term it MPS BCD Gen 6 because we have a variation in this process technology. So you can consider it like we rent the kitchen, but the recipe is ours. So we have our own MPS BCD Gen 6 process technology. And by this, you can see as we move above on the maximum operating voltage, we are still better compared to the foundry process or the competition process. So as we move upwards, we need to target a low RDS on times area. So the lower the better. So any lower values are vital for better efficiency and better thermals and beyond. So with this MPS BCD Gen 6 technology, we enable 20 to 35% smaller FET size, and also 15 to 20% more power. So higher power density, but in the same package. And next one is the packaging technology, the flip chip packaging technology. It's not new. It's been around for some time now. And in a flip chip, the die is flipped face down, and the signals travel through the solder bumps directly to the lid frame. And because these use the tiny solder bumps, this is connecting directly to the substrate, and hence shorter signal paths, which means, yeah, shorter than the wire bonds. And this will in turn then lower the parasitics and gives rise to better performance and capability to switch at higher frequencies and also faster signal transfer. And also because the die is flipped face down and the back of the die is exposed, this they can then connect to a heatsink, and heat directly travels directly out of the chip. And also the copper redistribution layer, that is the metal layer that is added on top of the die to reroute the signals from the internal pads to the bumps, and this will enable also low resistance current collection. So, in addition to having superb, great electrical performance and excellent thermal performance, this also enables to have smaller footprints, meaning larger dies in a smaller package. So now we went through all the key technology differentiators that MPS has, and now we'll move on to the products that we focus on when we power up the SoC core rails of high performance compute platforms. So here, the digital controller plus driver MOS solution. So this is a highly efficient and compact solution, majorly because, so first, the controller is digital, based on digital control and not analog. And with digital control, you have easy compensation, so you don't have to play with your resistors and caps as much. And with these advanced PWM techniques, you have faster transient response and better current balancing between the multiple phases. And also because it's digital, it's easy to configure, there's flexibility, and also within the controller, there's real-time monitoring and reporting, and also a comprehensive set of protection features. And when it comes to the DRMOS, so this is a monolithic design, which means it's integrated, so it's fewer components and more robust. And because of this specific monolithic technology, we are able to reduce the switching losses and able to have higher efficiency and also better current sensing accuracy. And all of this in a very compact design with fewer external components and cost-effective solution. So this is an example of a robotic SoC power tree. So for example, having a 48-volt battery, having a pre-regulator, stepping it down to 12 volt, and then here comes the controller and driver MOS, the MPQ2967 and the MPQ86960. So here to the SoC, we have four rails going into the robotic SoC platform. Each rail rated at 50 amps, 50 amps, the third one at 80, and the fourth one at 30. So here, because the controller is a multi-phase controller, we are able to use the driver MOS, for example, in a 2+2 configuration for 50 amps and a 3+1 configuration for 80 and 30 amps, respectively. Yeah, so the next one is another example, but for a more compute intensive humanoid robotic SoC. And here we go with the controller, the MPQ2967, but with an 86750 driver MOS. And here as well, we have four core rails, and we have the driver MOS in a 2+2 configuration for 103 amps and 65 amps, and also a 6+1 configuration for example, for 420 amps and 55 amp core rail. And this is another example, an application block diagram for with two-stage conversion. So, for example, you have a 48-volt battery, and in order to step it down to example 5-volt, we also have solutions. We have a three-level controller plus a driver MOS-based solution for 48 down to 5. And then from 5 down to the core is again the multi-phase digital controllers and driver MOS. So, for example, here we have six rails going into the robotic SoC, and we have the MPQ 86760 driver MOS in a 3+1+1 phase, and the 86760 here in a 1+1+1 phase. So a high-level overview on how we kind of map the controller and driver MOS in the whole spectrum. So a 48-volt battery with a front end. So we have a controller plus three-level driver MOS to step it down to 5 for power levels less than 300 watt, and a controller plus gate driver plus discrete FETs for power levels greater than 300 watt, and then stepping it down to 5 or 3.3, and then having the multi-phase digital controllers and the driver MOS, which are rated at, we have solutions at 25 amps, 45, 60, and also 90 amp per phase, and then going down to the core rails. And so the next spotlight is on the POLs, on the point of loads. So here as well, we have two options. So we have both 22 volt and 6 volt rated POLs. So depending on your battery, and so here we have 22 volt POLs for a 12 volt, going down to 30 amp. 40 amp per phase, and then we have 6 volt rated POLs also going down to the SoC core rail. Okay, so coming to our roadmap of products that are currently available now. So on the left-hand side, we have our controllers, MPQ. So for example, the first one, MPQ 72957. So this is a 4-rail and an 8-phase controller, which with EVS bus and also I2C interface. And the 2946 is a 3-rail and 8-phase controller with the I2C interface. The 29125, again a 3-rail 8-phase but with SVI3, and 2967 with 2-rail and 4-phase with PWM WIT and I2C, and the 2977, which is a 2-rail and a 6-phase also with I2C. And the next one is the driver MOS, or the power stage, the integrated power stage, or the driver MOS. And for example, the first one is MPQ 86960, which is a 22 volt and a 50 amp driver MOS. And for example, the 86940 is a 22 volt and a 40 amp. And the 86760, for example, is a 6 volt and a 45 amp. So we have products for both 6 volt input and 22 volt input. And on the far right is our high current converters or point of loads, and the MPQ 29261, which is a 22 volt input and an 18 amp output POL. So here as well, we have both 6 volt and 22 volt versions available. Yeah, so coming to an example of the multi-phase controller. So this is the MPQ 2967, and this controller works together with the integrated power stage or the driver MOS to complete the multi-phase voltage regulator solution. And also has all the benefits of the adaptive or advanced constant on-time PWM for lower output capacitance and better EMI. And because it's based on digital control, so this is more flexible and better optimized tuning, and also faster design cycles. And also certain other features like on-chip multiple time programmable memory to store and restore device configurations. And also the device configurations and fault parameters that can be configured or monitored using the PM bus interface. And so this supports multiple voltage regulator devices, and will use the same PM bus interface. And also all the comprehensive protections like under voltage lockout, over voltage protection, under voltage protection, over current, and over temperature. protection also with that telemetry flag, and yeah, as I mentioned, so all the automatic loop compensation, so phase shedding with and without yeah, discontinuous conduction mode to improve overall efficiency, and also separate enable for each rail. So all of these features in 6 by 6 QFN packaging. Okay, so the next one is the driver MOS. So we've taken the 86960 as an example. This is a 50 amp output driver MOS, and of course, the monolithic design for integration will offer higher switching frequency and reduce your inductor and cap size. And has a wide operating input range, 3 volt to 22 volt with a 5 volt VDD, and current sensing built in with our trademark technology called the AccuSense current sensing, and also temperature sensing, and current limit protection, and over temperature protection. And all of these at a LGA 5 by 6 packaging. And yeah, the next one, the MPQ 29261, which is an 18 amp output and a 22 volt input, high current power converter, also based on the adaptive constant on time algorithm, and yeah, digital control, and also more or less the similar features as the digital multiphase controller. And the packaging is also a 3 by 4 QFN package. So that is it from my side. Thank you everyone for your attention and listening in.